Eternal storage. A Solidity design pattern for upgradable contracts. In this video we are going to study the eternal storage pattern. With this pattern, a Web3 can start working with a new contract that is replacing an old contract, but without losing all the legacy data. Let's say that we have a Web3 site to store the user favorite city on the blockchain. The website and the code of the Solidity contract could look like this. We can store the cities in a map using the user address as key. After some time, we decide that we need to store not only the user favorite city, but how many years have she been living there. In this example, we decide to store the years that the user has been living in her favorite city in a new map. But what would happen when we deploy this new contract? We cannot overwrite the previous contract, which is immutable on the blockchain. The new contract will be deployed to another address. We can make our Web3 to connect to the new contract, but all the data stored in the old contract would not be present in the new version. We can try to hotfix it by transferring the data of the old contract to the new contract upon creation. This can be very difficult. Old contract properties might be private, maps keys should be passed as constructor parameters. And even if we devise a way to restore all data from the old contract, the transaction could be very expensive, or even run out of gas. This is not a good solution. Let's try yet another approach. We can split the contract into two, one to store data and another for the logic. Then, you can replace your old logic contract with a new one, and still use the old data contract. This would be the data contract for our Web3. We still have a map for the user's favorite city, plus a getter and a setter. And this would be the logic contract. We keep a property pointing to the data contract that we initiate on the constructor. For the second version of the contract, we write another data contract, this one storing the years the user has lived on her favorite city. The logic contract of our second version will use the data contracts of the first and second version to store and recover the cities and the years lived on them. The data from the first version will still be accessible. Even so, this is not an elegant solution and it's difficult to maintain. We finally arrived to the eternal storage solution. We are writing a separate contract to store the data, but we are doing generic enough so that it will not need to be upgraded. The data contract, or storage contract, is deployed once and will work for every subsequent logic update. Thus, eternal. This is how it works. The eternal storage has a map for every data type, along getter and setter functions for it. In the logic contract we no longer need to have properties to store data. We will use the maps on the eternal storage contract for that. The clever part is what we use for the map keys. We will concat the name that we would give to the property if we didn't use the eternal storage, with any other relevant parameters, like user addresses, array indexes, etc. We will then make a hash of the resulting string, and that will unequivocally identify our data in the eternal storage maps. Now, let's have a look at the second version of our contract. We are passing the eternal storage contract address in the constructor. In this way we would have already available all the city data. We just encode a new key to save the years lived in our favorite city. But what if we have properties with complex types, like instruct? Let's explore one example. Say that we want to develop a third version of our Web3 to store our favorite place in our favorite city, categorizing it, and stating whether this is a free place to go or not. We will save this new data in a struct with a couple of strings and a boolean. We will use the same technique to calculate the key for the map. We can encode the struct and use the bytes map to store the data. Now that we know what the eternal storage contract is and how to use it, let's have a quick look at implementing access control. Normally we would want only one contract to be authorized to modify the data in the eternal storage contract. Not everyone should be allowed to fiddle with our data. Also, we would need to have some sort of ownable functionality in place to tell the storage contract what contracts are authorized. This is how the workflow goes. The owner, a user or organization, deploys the eternal storage contract. She then deploys the first version of the logic contract, v1, passing the address of the eternal storage contract as parameter. Then, the owner sets the recently deployed contract as authorized contract to work with the eternal storage contract. From this point on, the v1 logic contract can work with the eternal storage to save data. At some point, a new version of the logic contract is developed, v2. It is deployed in similar fashion as v1, passing the address of the storage contract, the same storage contract, as parameter. Then, the owner sets the authorized contract of the eternal storage contract to v2. From this point on, v1 won't be able to save any data in the eternal storage contract, and v2 will be able to use it to store data. We can achieve this by adding little more than some basic ownable functionality and a modifier that checks that setter functions are called by the authorized contract. Implementing the eternal storage patterns adds boilerplate code that make reading the contract more difficult. We can improve it using libraries, moving the complexity of dealing with the eternal storage contract away from the logic contract. Moving all the key generation, encoding and contract management to a library, and taking advantage of the using directive, we can make the code looks like if the eternal storage address would have methods to store and retrieve our data, greatly simplifying the code readability and improving the cohesion of the contract. That is all for this video. I hope that you have a clear idea of what the eternal storage pattern aims to achieve, and some general idea of how to implement it. Don't forget to check the code of this video in GitHub.